Okay, welcome to our session on applications. Our first talk will be from Jozsef Bakosi, who is a research scientist at Los Alamos National Lab, and he'll be talking about quinoa, which is a new framework developed on top of CHARM for computational fluid dynamics.
Does it work? Good. Thanks, Sam. I'm from Los Alamos, as Sam said, Jozsef Bakosi. I'm going to talk about a code that we have been developing for, well, about 6 months officially, but I've been working on this for a few years in my free time, nights and weekends before that. So I'd like to acknowledge the team members first, some of whom are here. Bob Bird, who is not here, but Christoph Junghans and Robert Pavel are sitting over there, and Jacob Waltz, who's at Los Alamos. And I had the privilege to work with two excellent summer students last summer, Francisco Gonzalez, who's also here, and he's at the aerospace department in grad school, and Brandon Rogers from University of Tennessee. So what we set out as a distant goal here is to write a code and then write it from scratch for the applications we are interested in. And that is a distant goal, what's written here in the center. So right now we have this grand vision of coupled large-scale multiphysics. Now, almost none of this is done yet at this point, but we're making steps. So the real goal is to have an application that obviously performs well on large computer computing large-scale physics, but for applications that are very dynamic. And so we're putting in adaptive mesh refinement, particles, and so on. I'll talk more on the details. And we want to do this in a way that, despite the complexity, it preserves the domain scientist's sanity in a sense that we don't want to intermingle too much code that require really different fields of expertise, because that's a disaster then. And so we want to outsource everything possible. So that's the agenda, philosophy, the infrastructure that we have so far. I'll talk about it, and then I'll talk a little bit on 2 of the 5 tools that we have at this point, and the future plan. So here's the philosophy: large-scale applications. With that in mind, we want to partition everything, assuming things like the mesh doesn't fit into a node and things like that. So be asynchronous everywhere, automate everything. That's including the build system as well as coding, testing, everything. And remember that everything fails, so fault tolerance. Keep that in mind. So our strategy right now is, I think, and anyway, in my experience, is that I think our approach is slightly different than what my little experience allowed me to see in this realm of writing multiphysics codes. And it's different in a sense that I believe when things like that start, they put a bunch of smart people in the room, and after some few meetings, there's lots of domain experts, and they start writing code. And I have a feeling, looking at the codes after that, the software quality and software engineering somewhat is a second-class citizen. So we want to change that a little bit. So we start the other way around. We do nothing. We do that, but we do that well. So we want to have a state-of-the-art production code. So they see the emphasis here is on production. So it's very important to keep the quality with testing, with the maintainability, and all that stuff, and keep it that way in the future. So what we have is we started a code not from starting based on any legacy code. This is from scratch. It's in C++ 11 at this point, and we use CHARM. We wanted to have the full freedom of exploring anything we can. So that's the only type of application we target is 3D distributed memory, parallel, fully synchronous, no And at this point, this is a single abstraction layer. So Charm++, non-SMP, the most vanilla type of application that you can imagine. So that's the pure MPI. The pure MPI kind of quote unquote, but in Charm. Actually, we do use Charm++ on top of MPI at this point. So that's the funding. I already talked about that. Take this with a grain of salt. It's a beginning of this project. So that's the infrastructure we have. And by the way, all these slightly blue text is in here. If you look at the electronic version, these are all links to those places. So take a look and explore. So about 50,000 lines in code, 20 plus third-party libraries, 3 compilers, so lots of tests, unit tests, regression tests. The whole thing is open source. Everything, all the laundry is out there on GitHub if you want to take a look. And we have a bunch of different continuous things. Continuous integration, that's a lot of testing, build matrices. We are using two different continuous integration servers. One is outside Travis, you probably have heard of that. TeamCity is what we use inside the lab. They're running different kinds of tests. And we have quantified test code coverage, also with 2 different tools. And we also do documentation coverage, API, Doxygen documentation. And we also use 2 tools for static analysis. It's showing us the diffs and all these fancy things. So we are hoping it will help to keep the software quality at a higher than usual level. And we also have continuous deployment, and so if you just want to try it on your computer, laptop, something, you just download the Docker container, log in, and you can start running right away. There's no need to build it or anything. And this is ported to Linux, Mac, Cray, different computers, Blue Gene. So here are the tools that we build. These are the 5 executables that we build right now. And I'm going to talk more in detail of the first 2, but let me start from the bottom. This is a mesh converter that's just used for converting different format meshes, and we're looking at unstructured meshes, so that's a useful tool to have. And by the way, everything is distributed memory parallel. It's all based on Charm++. So the other one, continuing from the bottom, we wrote a unit test harness because we wanted to have full flexibility of what kind of test we write. And also how many tests we can run in parallel. So we can test serial, MPI, Charm++, bulk synchronous, asynchronous, all kinds of tests. So for that flexibility, we just pulled our own test harness. And RNG test is a random number generator test suite that can subject the different random numbers that are available for Monte Carlo simulations from different libraries, subject to statistical tests. And so we can attach a label to it, to each of them. That's the price, that's the computational cost, and that's the quality of the generator. So later on, the users who do large-scale Monte Carlo, they can have a good, educated guess what random number I should or shouldn't use for a given simulation. So the first 2 part here, Walker and Insider. Walker is a particle solver at this point. It's a mathematical tool, and Insider is a partial differential equation solver for 3D unstructured meshes. So let me start with Walker. And so the equation here that we solve, that's written here in the first line, the first equation line. And that is a Fokker Planck equation. That's pretty similar to the Vlasov equation of plasma physics or Boltzmann equation of kinetic theory. What's interesting about this equation is that this y vector can be very large. If you take a turbulent combustion application, that could be the species concentration. You can have hundreds of species, and in that case, that dimensionality of this equation is very large. So you want to solve it with Monte Carlo, ideally. That is a system of stochastic differential equation that is statistically equivalent to this Fokker Planck equation. So it's a particle solver. It's Monte Carlo, and at this point we can evolve with millions of particles in time, and then compute statistics. And we use that actually in production already for another project that I work on, that aims at developing the theory and the mathematics for modeling, mixing 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 materials in turbulence. Okay, so I thought for this audience, what's interesting is more like how we use charm ++. So this is the DAG. It's not a hugely complicated DAG, but this is a DAG that we use for a single time step. The orange field boxes mean that's a global synchronization point. So that ends up in a reduction to a single char. And then we have two, and then the orange non-field ones are partial synchronization points. So these are the different tasks that we have to do for a single time step. So we advance the particles, we compute ordinary moments only when the particles are advanced, of course. Then you want to compute central moments like variance, skewness, and all these things, whatever the user wants. That can only be computed about the ordinary moment, of course, and so that's the relationship. But in the meantime, we want to estimate histograms, and those are different types too that we can do, and depending on what the user wants, ordinary or central PDFs. And then, of course, we want to write these statistics out to file, and the PDFs, and then finally we decide whether we want to continue with the next time step or not. So and of course you want to have the option to overstep all these, because not every time step you want to save all these things. So what I find, this is not very complicated as I said, but what I find interesting is that this is very, I find expressing this DAG pretty expressive in the DSL you guys have in the CI file to express this. And if you look at the actual code, I don't know if this is going to work, but I like to click on it. Can I allow? There, that goes to GitHub. So with some documentation, you can see that, oops, here. Wow, this is pretty sensitive. That's pretty much the whole thing, starting from here. That's fine. So the point I want to make here, and you can click on your computer and that will work better. The point I want to make here that all this logic is expressed in about a screen line of code. I find that short, expressive, and I think it's reasonably easy to work with it too. So that's the only point I want to make here. Once you have the visual picture of the algorithm and the correct dependencies, I find it relatively easy to express that. I don't know how that works with other runtime systems, but what I've seen, I like it, but I'm biased because that's pretty much the only one I work with. So anyway, this is a weak scaling graph that's somewhat unusual. There's a huge dip in it. I like it, I take it, but this was about 2 years ago when I did that. So I was able to reproduce this. Obviously, the ideal would be to continue here with this line, and then we got so much better suddenly here. I'm not sure why. This was reproducible at the time. I think it was a different day, a different constellation or something. I'm not sure how to explain it. So I got to reproduce it. I got to run it on a different computer and so on. But also another point that I wanted to make here is that to have this reasonable, good performance, what was absolutely crucial here is you guys' help with doing the custom type reduction that on the classes and object that store these PDFs. That's under the hood. That's a hash map, and we used the tree-based aggregation in Charm, and switching to that was the real key for the performance. Okay, so this is where this is going. So at this point, as I said, this is a mathematical tool. We'll integrate. Well, right now we're integrating this in time. So it's a particle code that doesn't have the complexity of spatial dependence. But when we do, we want to do this with an unstructured mesh instead of kernel estimation. For various reasons, we want to look at complex geometries first of all. So here is an example of a discrete PDF that you can compute. That's That's a histogram of 3 different scalars, and the height of that at a given point gives you the probability of the concentration of the 3 different species that could be in a given cell. So that's an example of what we want to be able to compute with this in every cell. And why do we want to do that? Because solving the flow equations for turbulent flows in this framework has certain advantages. Having to approximate less physical processes is one of them. For example, highly nonlinear chemistry. And so here's an example of what I've done with this in the past. And that's again as a 0-dimensional flow. What happens here is this is a Rayleigh-Taylor instability that I computed in time, and you got a cube, and you have heavy and light fluid, and initially that's at quiescent state, and then you have an external gravitational field, and you let it go. So initially that doesn't move, but then potential energy starts getting converted to kinetic energy, and then depending on the configuration, the flow undergoes transition to turbulence, fully developed turbulence, and then once all the potential energy is converted to kinetic energy, it decays due to viscous dissipation. So that time accurate process is relatively hard to represent with a statistical engineering model. The goal is, of course, we can compute this with DNS, direct numerical simulation, without any approximation, but that's a lot more expensive. This takes about a second to compute the whole thing, and that's maybe a week with many processors, right? So that's the order of magnitude. This is an engineering model, is what it comes to be. So this is just another manifestation of the same process. This is a mixing process as it's portrayed by the evolving probability distribution function for the fluid density. And that starts out with a double delta. The red one here, that represents unmixed fluids. And as time evolves, it goes through the different colors, and then the bimodal distribution turns into a single bounded Gaussian-like distribution. And then eventually the full limit state is represented by a delta in the center. That's when everything stops. So this is just an example of where we're going with this, but there's a lot more work done. This goes back to my PhD, where I did this with meshes and all that, but now we want to do it large scale. So I'm going to talk about now the other tool that we have funding for here with this project that we're working on, and that's the other one, Insider. So that at this point is a partial differential equation solver for 3D unstructured meshes. We use tetrahedra only, and that is also a Charm++ native Charm++ application. But now we use 2 MPI only libraries, Hyper and Zoltan, for linear system solvers and preconditioners later, and the static initial mesh partitioning, respectively. That's Zoltan. So at this point, we just put in a simple Navier-Stokes solver for compressible flows. Nothing fancy, single phase. It's the simplest you can get. That's not the concentration of the project. We solved that with finite element method, and we use flux corrected transport. I'm just going to have one more slide on this, because that's interesting to understand why we do that for a later slide that I want to talk about. So we have asynchronous linear system assembly, and for now 5 per rank I/O, which is okay, but doesn't go to very large core counts, of course. So we're working on that. So right now we're working on putting in adaptive mesh refinement, and we're going to use that as a vehicle to explore how we can keep and improve the scalability into large number of cores and large problems. So here's what I promised on flux corrected transport. It's just a single slide, very high level. That's a technique of CFD, computational fluid dynamics, and it's used for whenever stuff moves from A to B, and you have a PD, you want to solve it on a mesh, and and because of this theorem that no linear scheme of order greater than 1 will yield monotonic, that is Wiggle-free numerical solutions, we got to do something about it. Otherwise, we get either these kind of solutions that are too diffusive, we lose the solution, or something like that that eventually blows up. This is, by the way, is just these objects rotate. So when you want to rotate back, you want to get back the original one. So you know the analytical solution. There's nothing physics in this, it's just a rotation. But that's a test case for this. So the solution for the problem is to use a nonlinear scheme instead of a linear one. And the way this is done with flux corrector transport is to combine a low-order scheme that's guaranteed to be monotonic and a higher-order scheme that's more accurate, but only far from large gradients. That would be the height at the edge of these cylinders. So when we combine it, we get something a little better than both of these, but not perfect. But anyway, that's the point here that I'd like you to remember for the next slide is that for a single integration, a single time step, we need to combine two different schemes together that one will depend on the other one. The low order is constructed from the higher order one. But before, I want to tell you a little bit on how the assembly of the linear system works. So we get a mesh. That's just an example, the complexity of what we're thinking. And so we do the assembly in two different steps at a two-level, using a two-level approach. So we use what I call lean sys merger, linear system merger. That's a charm group. And so that's guaranteed to not move across, that doesn't migrate. And the job of this object is to interact with the MPI-only library, in this case Hypre, and assemble this system and collecting the results, the contributions from the workers. The workers are what I call carriers. And this is a charm array. That's the one that, these are the guys that hold the chunk of the mesh, and they perform the heavy lifting. They will perform heavier and heavier lifting as we add more physics on the mesh. And then, as you can see, the goal is, or the assumption in the design is that these can migrate at some point. It doesn't migrate right now, but it will. And it can be various numbers at different PEs. So once the contributes, the operators are computed, they get they don't get communicated. They get sent to the given lean sys merger that happens to be on that where the worker happens to be, and that gets collected. And the communication on the processor boundary is done between only the lean sys merger objects. And then once the system is assembled, we hand it over to Hypre, get back the solution, and then we continue. So here's how it looks. Here's how the DAG looks for a single time step here. And that's a lot more complicated. That took a lot more time to debug too. And as you can see, there's a few synchronization points here too. And I'm not going to go into detail with this, but you can identify the different parts that you probably know what needs to be here. You compute the size of the delta t, for example. There is initial conditions. There is boundary conditions on the left side, the right-hand side. And we got to transform the data structure into something that Hypre understands, both left-hand side, that's a compressed row storage sparse matrix. And then once everything is done, we have the left-hand side, right-hand side, and all that's ready. Then we can solve and then update and then go back to the beginning. So what I want to point out, the aux solve is the low order solution. So this is solving two systems combined where the lower order is derived from the higher order. So that's what makes it a little more complicated. And again, I'm not going to click on this. This also fits on a screen. You can click on it on your computer, and that has a lot more text and documentation of why I'm doing the way that is that way. But again, the same point I can make here is that I find this pretty expressive. I think it's pretty reasonable to work with. And here's an earlier here's about a year old or more too. Strong scaling study that I did. I pushed this up to 4,000 processors. This involves the initial I/O, the read and write, and the setup as well. So you can see this is very, very nicely balanced. This is 10 time steps here. That's from projections. 10 two-stage time steps. So you'll see the linear system, I think, is the yellow, and the right-hand side is the green. The right-hand side, the physics calculation, really. And what I'd like to point out here is that there is this initial setup stage that involves mesh node reordering that has to be done in a distributed and parallel fashion, and that's not very obvious how to do it. That's because we need a different order compared to what's in the file. Because later then, if you don't do that, then the communication cost is just too much. So, and that algorithm is fairly complicated. It's more complicated than what happens later. But, what's interesting is that the different processors have each very different load. So I think I like this a lot. It's still, there are some gaps, but it's nicely overlapped. So I'm very happy with this. And I think with more processors, that's even better. I'm not sure, but we'll have to look at it. Here's another one that pushes us a little bit to about 40,000 cores. And that's with a little bigger mesh. And that's, the two colors just mean different initial partitioning algorithms. There's not much difference between them. It's just two different ones that are available in Zoltan. And what's interesting here, what I want to point out is that this is, it's not too bad. There's room for improvement, of course. And around 40,000, I couldn't run it longer. I just break MPI on a machine or something like that. So it would go further with bigger mesh too, but I just haven't been able to do it technically. So again, what I want to emphasize here is that this is the pure MPI equivalent of using charm. So there's no migration, there's no SMP, there's no OpenMP, there's no vectorization, there's nothing fancy here. We just made it sure the algorithm computes what it needs to compute. And that's not a bad start, I think. I think that will definitely become better. And as we want to push it to larger meshes, this is about close to 1 billion cells, but we definitely want to see how far we can push this. So this is where we're going with this. So right now we're implementing adaptive mesh refinement. We're pretty close to being done with the refinement part. And of course, the next step will be de-refinement. So we can follow a feature that happens in a flow, for example. And we want to use that as a vehicle. And that's the main goal of the project, to explore what the runtime system can do for us and what we can do for the runtime system. We'll see. And how we want to use the runtime system to keep and possibly improve the scalability for large cases. And so we're getting ready to implement this in parallel. We started the AMR part separately so that we understand the algorithm, but we're getting ready to do this asynchronously and distributed memory parallel. And then here are different directions we are taking this. We want to do asynchronous I/O at some point, possibly CK I/O, both read and write. And we always have summer students, and we explore various things. Vectorization abstractions will be a couple of students working on this summer. And also we want to explore root. That's a framework coming out of CERN for very large data storage and statistical analysis and visualization. And by the end of the project, we promise that we would like to demonstrate fault tolerance. We just want to rely on Charm++. So, and also we want to teach that to ourselves, how to use it. And these are just the different refinement cases. That's the paper. That's also a link. You can click on it. By Jacob Waltz. He's done this a long time ago, as you can see, 2004. So these cases are restricted to not all the potential combinations, but so that we never end up with hanging nodes, because that would require modifying the solver. And so this is also part of separating concerns. So And that's just the acknowledgement that I have at the end. These are all the third-party libraries. Click on the links if you want to learn more about them, and the compilers and the tools and all the wonderful tools that we use outside and inside the lab. And finally, I want to acknowledge the funding from the Los Alamos LDRD office, without which we wouldn't be here, and I would still be working at night and on the weekend on this. Thank you.
We have time for a few questions.
I was wondering, the inciter structure dagger thing that you showed didn't look structured to me. How did you express? I mean, is it not structured, or is it structured? I just missed it. That is single entry, single exit graphs. Can you just go back to that thing?
Yeah, I think so.
Looked like they were like the...
Okay, not every part is there. I think, so those are two function calls that the chars, the carriers, call into.
Right.
The CH row and CHBC. One is boundary conditions and one is the indices of the rows of the matrix. That's coming from all the different carrier chairs. And then after, that's basically a single entry.
I see.
And then that is a single, and then we go back.
Okay. Oh, I guess, okay, as long as you say so, I will look at the code later.
It's only
that's
part of
fine.
the whole thing.
But it wasn't a problem. That's structure dagger was adequate for what you needed.
Yes.
Okay.
I think so. What I had a hard time with is identifying these orange blocks. Not to identify it, that I was familiar with what needs to happen, but how to express that better, because what these mean is that either a direct visible function call that I'm doing a reduction to some single char, or they lead to that path later. That might not be on this figure, and sometimes it's later on that happens. But I need to keep track of that since it goes to the same, and there's multiple ones. And so we had this discussion on the email list where the order might be important. And if you can't guarantee the order, that leads to a problem even in MPI. And so that I had to actually add in additional DAG logic to ensure that. Nice. Without that, sometimes I run into it. That was the hardest part to debug there. I think it works now. Yeah.
So first, thank you. I've shamelessly stolen many of your CMake files. They've been very useful. Yes.
I'm glad you can use it.
Very good. So you're using finite element?
Yes.
Is that? Okay. And so then I don't know if you've thought about this, since you seem to be, we seem to be taking the same approach, get the code working first and then worry about the physics. But in terms of refinement criterion so we're using discontinuous Galerkin, so it's sort of similar in some respects. Have you thought about what refinement criterion you would use to split elements and these kinds of things?
We're probably going to use the simplest one first, and that is based on the assumed truncation error coming from discretization, which is just a linear finite element at this point. So since the shape functions in our method, the finite element shape functions are linear, the error is always second order. And so we have an error indicator that's normalized between 0 and 1, and it's basically dependent on the second derivative across an edge.
Okay.
That's what we're going to use as an indicator. If that's close to 1, there's a threshold for refinement, above which you tag for refinement, and there's a threshold below which you derefine the given edge.
Is that one part of deal 2? I can't remember. They have are you familiar with deal 2?
So?
I think that's a finite element solver that they have a bunch of different refinement criterion, and they do things like that. So
that is the art in AMR, and that's what makes it somewhat hard to use for engineers who use these codes. And there is somewhat active research in it, and it's not bulletproof. There are some features in some flows that's non-local, so this will not capture it. But our concentration is to get this working first, and then do the computer science research with it, and then hopefully we can make it useful for these use cases too.
Okay, thank you.
Okay, I think we'll move on to our next speaker, but let's thank Jozsef one last time.